Similarly, if I go for defining a language having odd number of A's, then how do you design finite state machine? Odd number of A's possible strings in the language are 1A, 3A's, 5A's and so on. At that time, can initial state be the final state? No, because epsilon is not the string in this language. So first we must have one compulsory A reaching the final state. So we have already designed initial state Q0 for one compulsory A going to state Q1, which is the final state. So by this FSM, first string is accepted, that is one single A. What about 3 A's? For that, what we have to do, 1A reaches the final state, second A will go to the intermediate state, that is Q0, and third A, it will go back to state Q1. So the same logic is applied here. When you have odd number of A's, it will go from intermediate to final. When you have even number of A's, it will come from final to intermediate. So finally, to reach the final state, you must come across odd number of A's. So this is a finite state machine designed for the language consisting of odd number of A's. Till now, we have discussed with only one symbol. Now, let us take some more examples wherein the alphabet consists of more than one symbol. So, in this example, we have A and B, two symbols in the alphabet, and the language containing either A or a B as its string. Then, how do we design a finite state machine? It is very simple. From initial state, one compulsory transition to A, with A reaching the final state, or from the initial state, one compulsory transition B to state Q1, which is the final state. This can also be represented as with one single transition having comma in between. This is equivalent to this finite state machine, either A or B, A or B. So both these finite state machines are equivalent. We have discussed a language consisting of even number of A's. We'll take one more language which is similar to it but consisting of two symbols in the alphabet A and B. The language consists of all possible strings where the string length is even. It means it can be either A or B, but the string length must be even. Possible strings in this language are: no occurrence of A or B represents epsilon, two A's string length is even, A B or B A string length is 2, B B string length is 2, A string length is 4. So similarly, it can be either A or B, but string length must be even. So how we design the finite state machine for this? First we have epsilon, so by default initial state is the final state. And what was the logic applied? If I come across one symbol, then it will be in the intermediate state. If I go for the second symbol, then it must reach the final state. So same logic is applied here. When I come across a or a B, it will go to intermediate state. When I come across another A or B, that is string length is 2, it will go back into the loop to Q0, which is the final state. So let us take up one example, AB. AB is a string which belongs to this particular language. Start with initial state Q0. A reaches Q1. For B, it will reach Q0, which is the final state, hence the string is accepted. Similarly, let us see how to design a FSM for the language containing all possible strings of odd length. Possible strings in this language are A, B of length 1, then string of combination of A and B of length 3, of length 5, and so on. Here also the same logic is applied. Start with an initial state Q0. For one input symbol A or B, it reaches the final state. That is, for odd number of A's or B's, it will be in the final state. When it comes across even string length, it will be back into the intermediate state. Let us take an example of string A, B, 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 E. So this is string of length 5 and this must be accepted by this particular FSM. Start with initial state Q0. For A, reach Q1, B, 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 and last A, it reaches the final state. Input string is consumed. It has reached the final state Q1. Hence, the string is accepted. So these are some simple finite state machines which we have designed. We'll see few more finite state machines in the next lecture. FSM is applicable in many of the domains. To name a few, it is used in vending machines, traffic lights, video games, text parsing, CPU controllers, protocol analysis, natural language processing, speech recognition, etc. Examples of these applications will be studying in detail in the future lectures. Finite state machine is of two types: deterministic finite state machine and non-deterministic finite state machine. In the next lecture, we'll be discussing these different types of finite state machine. Thank you.